Hi, and welcome back. And we're going to continue our study in statistical mechanics. And last time we really kind of derived entropy, and we kind of started talking about the number of configurations a box can be in. And just as a reminder, we talked about sort of the number of particles, the volume, and the energy. So this is our macro state. And from that, we were able to build up the sort of the total number of possible configurations, and we called that sort of capital omega. And when we went through the math, we then saw how the rate of change, a partial of the number of states here, was 1 over kt, and we ended up, of course, taking the natural log and squeezing it in there. And so this is actually where temperature comes from. Back to our earlier discussion, humans, we don't feel temperature, we feel heat. So temperature is this thing that we can clearly measure with a thermometer, but when we try to understand it, it's always like, what's dry heat versus hot heat and things like that. So we have sort of the definition of temperature, and we observed about it by taking two systems and kind of pushing them together. And so this time for the next round in this, we're going to take two systems, A and B, and we're going to push them together. There's A and B. But we're also going to imagine that this barrier in between them, yes, so thermal contact, but that this barrier is actually floating. So imagine this is a piston that can move back and forth. Okay? And so, when we just look at the rate of change of kind of the total system, right? So the combined system, A and B, we would have from the natural log with respect to energy on 1 compared to the rate of change of total energy versus 2 are going to be equal. That's our equilibrium condition. And honestly, that just led to 1 over T1 is equal to 1 over T2. So the same thing's going to happen here. The two temperatures are going to come to a thermal equilibrium. But because this piston can slide back and forth, we also have another condition. Maybe I'll do this one in green to sort of separate it. And so this condition is going to be the partial, again, of the natural log of the total amount of states with respect to the volume, 1. And we want to, we'll effectively say that this will be, to come into equilibrium, the natural log, volume 2. Now, the hard part here is that we kind of know what dE, the partial of this compared to E. So I actually want to say that this is, to back this out, this is going to be the same as the natural log with respect to E, and then you're going to get this del E, del V, right? And so kind of chain rolling it. Now, I'll write it over here because I'm going to come back to it here in a second. But I actually want to go back to where we've already been and said, if you remember the equation of thermodynamics, dE is T ds minus P dV. And remember we said this is our Q, so actually, we now have Q as the integral of T ds, just like we have work is equal to the integral of P dV, such this is, this is Q minus W. Okay, so we have this, and really, if we're taking a look at the energy dV, well, what is that? Which one is d energy dV? Well, if I write this equation down here, dE is equal dE ds times partial s plus dE dV partial v, guess what? You then have that dE dV is equal to negative P. So you actually have our definition right there without having to go any further. By the way, a little fun thermodynamic joke. Make sure you're laughing, but thermodynamics is tedious. Nice. So we sort of have this equation. So we know what this is going to be. So this is actually 1 over T. I'll keep the KT in there. And this is just minus pressure. And so this entire equation is then going to balance, right arrow, this is going to balance into P1 over KT1 is equal to P2 over KT2. So we already know the temperature is going to be equal, and this means the temperatures and the pressures have to be equal, which is basically going to turn into the pressures have to be equal. So hopefully none of that was surprising, right? If I had two systems and I brought them together with a piston in between, the temperatures would balance and the pressures would balance. But so we get that very naturally. Hopefully that was not a surprising experience, but it's nice to show that the formalism we have here with sort of counting the total number of states, of course, we keep the natural log of it, but that it's resulting in the things that we expect, and it's actually creating these thermal equilibriums as you would expect. Okay, and so last one I want to kind of cover, and I think I've already showed it once before, but I'll just sort of highlight it again. That you have this TDS equation, and let's see, I'll come down here and do it right here. I'll draw a line, but this is dE. So what happens again if you did dE plus PV? Now remember, this is actually our definition of enthalpy, H, and so if you expand that out, that's dE. Well, that's this whole thing. That's TDS minus PdV. But then you have this PV term, and so you'd have to chain rule it. So you would have a plus PdV, and you would have a plus V dP. And I hope you see that that one and that one cancel. And so you are left with dH is equal to TdS plus V dP. And so this is, again, partial of why the choice of using enthalpy in some problems is actually really convenient, because it's, you may have this term that's constant pressure. Like we showed last time, kind of crossing the boundaries is helpful. So just a reminder of that's where we're going to have a lot of these sort of thermodynamic variable changes. Okay? And the easy way to sort of draw and remember this, and we'll come back and kind of share this many times. This could take a little while to sink in. And so I'll use the standard U. I know a lot of times E and U are sort of being repeated a lot. This is our internal energy. Okay? This is enthalpy. And what we're doing in going in this direction is we're adding PV. So it's U plus PV is equal to H. And then we'll actually see that going this direction, we'll subtract a TS, and we're going to get F and G. So this is free energy, Gibbs free energy, and Humboldt. So we'll come back to that, and we'll see some examples of that probably in the future. But this is ultimately we're sort of free to do these Legendre transformations to make our lives easy. And really some of the reason I like going through this math, or actually fully believe that you have enough math in undergrad that this is nothing that this is crazy. It's actually because if you understand where some of this math is coming from, and you have that right tool, then what it lets you do is it actually lets you, step one, solving any thermodynamic problem is actually it's actually listing out your assumptions. Like, well, what is being held constant? Do I have any heat? You're sort of just listing out your assumptions, and then after you listed out your assumptions, you're sort of free, if you will, to choose your own adventure to solve the problem in the easiest means possible. Of course, you can brute force things, and God bless somebody who wants to try and brute force things. But a lot of this really comes into just solving the right problems, and especially when we sort of circle back here to thermodynamics and kind of the standard undergraduate thermo, and we're looking at cycles. Some of this is it's actually just connecting the dots. It's solving for the next unknown step. That's all you're doing, and just kind of fully connecting the dots, and then there you go, right? So this is that's why I really find treating the math at this level shouldn't be too scary. And again, if this is scary, go back and look at some of your undergraduate math, some of your calculus, some of your differential equations. I know you've taken it. There are some great math textbooks, math for engineers or math for physicists. They're going to be a good reference for you. Some of this is just a little too rusty, or you didn't pay great attention because maybe it was a math professor teaching you, and they didn't have enough examples to real world to kind of connect it for you. So I'll just sort of write a few more things here, and then we'll take a look at going to come back and take a look at a few more things. But as a reminder, because of these transformations, you have sort of the specific heat, which is T and then ds dt, right? The whole thing, that's equal to the rate of energy with respect to temperature. And so really the sort of the changing internal energy with respect to temperature is what we would call the specific heat. But it's just this sort of formula. And same thing here, you're going to have what we'll call specific heat, Cp, constant pressure. It's T and ds dt, whereas this one was holding sort of the number of molecules and the volume constant. That's an S, by the way. This is holding the number of molecules and the pressure constant. Well, that's actually the same thing as doing the E plus PV dt, holding N and pressure constant, which is dH dt. And so, you might hear in a basic undergrad class, we write these constant volume, specific heats, constant pressure, specific heats, and people always get caught up. This is what I'm doing, the warning. People always get caught up on, oh, well, I used CV because my volume was constant, or I used CP because my pressure was constant. I really actually wish that the entire community would write this as the specific heat for internal energy and the specific heat for enthalpy. That's actually the better way to do this nomenclature. And so if I can get anything across to you that would help you, is you should be using Cp when you're looking for enthalpy, and you should be using Cv when you're looking for internal energy. Okay, so I'm gonna wipe this off and come back up with a few more things. We'll see you here in a second. Okay, so last part before we sort of complete this little sojourn into statistical mechanics. And the reason why I wanted to do this again is I find the graduate level, even just at chapter 1, we may come back and do sort of all the rest of the statistical mechanics here towards the end of this book club, kind of 2 through 5. But the reason sort of chapter 1 is important is because just I don't find what we do in the world of undergraduate texts to truly be enough for people to get entropy. It's worth understanding that you're kind of counting out the systems and you're looking at the total possible ways to rearrange. And now, I know if you come from the world of physics, you're going to start off almost from a pure quantum mechanical point of view, and you literally are going to count the number of states and all this and kind of get to this point where, oh, good golly, I'm now counting 10 to the 23, and it turns into what we call statistical mechanics. But the value here, in at least digging down, even if you're just an engineer, is to just get that little bit more appreciation of entropy, that's the number of states, that there's a maximization of it, right? So we're actually seeing where it's a maximum for the total system, and then we can go back and relate the two, and we find these equilibrium conditions. And so it's super important. So the last step actually I want to talk about is ideal gas. And again, from this framework now that we've actually built up a little bit of statistical mechanics, ideal gas actually has a more natural way to describe it than just sort of dropping some equations on you. Okay, so for an ideal gas, what we actually are talking about is our molecules are solid spheres, and they're free to fly around and sort of bang into each other. And they're all free to have different velocities going in different direction. Now, if you somehow can track all of these, billiard ball mechanics and add them all up, you're going to get an ideal gas. Is there an ideal gas out there in the world? Actually, the answer is no. Most of the things that we would treat as an ideal gas are actually like a diatomic molecule. And so, even in hydrogen, here's H2, right? Hydrogen would actually have 2 molecules and a bond in between, which means that the bond can go back and forth. You can have vibrational energy. It can rotate, so you can have rotational energy. So even this would not be quite accurate. And then there are also kind of van der Waals forces in between the molecules, which break all of this down. So really, ideal gas, you have to just start off with this idea of it's this mythical billiard ball banging around. And it's going to give us the decent approximations. But just beware. Again, just beware. All of these gases are going to have portions where ideal gas is going to completely fail. Especially me as a rocket scientist, right? You pretty quickly get some pressures and temperatures for which ideal gas doesn't work. You literally have to go look up the properties and thermodynamic references, right? Even if it's nitrogen, which we usually claim is an ideal gas. Okay, so in the book, if you've had enough quantum mechanics, go ahead and read in any one of these statistical mechanics chapter 1. Read through the partition functions, read through how we're counting up the quantum states. Read through that if you're familiar enough with the quantum mechanics. I'm just going to sort of end with the punchline, which is in this ideal gas system, if this is what's happening and there's no sort of interaction, you actually have total number of states is going to be proportional to sort of the volume raised to the n being the total number of molecules in the volume. What's the total number of potential configurations? What's all of the ways that these gas billiard balls can have energy distributions and banging around. Okay, so that's why it's a big number. It's usually one of the reasons why we take a natural log of it. Although natural logs also are pretty easy from a differentiation point of view. And so what I want to then show is that, we already kind of defined from last time that P over T is the change in entropy with respect to volume. Remember, at S compared to this, as a reminder, S picks up that K, so we don't have to keep track, natural log of the omega. So the partial of entropy with respect to volume is P over T. We derived that a little bit earlier. And so if you do that, right, and remember this K is natural log. And so actually let's walk through this. So if that's the case, I'll do it in green, then you actually have S is equal to K natural log of V to the N, and there'll be some other stuff in here because it's proportionality constant. I'm not going to worry about all the rest of the stuff. Just there's some other junk in there. Well, the property of natural log of this N can come down, so this is actually Kn natural log of V. And so ds dv, then if you take a look at that, would just be that, the natural log becomes a 1 over V. So this is just Kn over V, right? And so that is your ideal gas relations. Now, this is usually not how we see it. We usually see the T up top and the V over there. So draw a line. Normally, this is written PV, and I'll just do the first version here, which is KNT. Well, it's not also the way we normally see it either, right? In fact, we would kind of lump all the rest of these constants together, and we would say it's actually nRT, where this is ideal gas constant. Okay? You may see it as P is equal to rho RT, because ultimately you can combine the number of molecules and you can switch this from the ideal gas constant sort of the specific for the molecule. So you may see it like that. So a whole bunch of different derivations, and of course I'm going to be careful the sort of the specific gas constant versus the universal gas constant. And so this is the form that we normally see ideal gas, okay? And so the other thing that we get from quantum, and that's why I like teaching on the ideal gas here sort of at the statistical mechanics point of view, we get one other really interesting piece from quantum mechanics, and I'll start drawing it over here. Okay, ultimately, we get that when you add up all of these energy pieces, you actually get that volume to the 2/3 times the energy is a constant number. Okay, and so that's interesting. And so if you go back and you say, well, P is equal to the derivative of E respect to V. Remember, there's that minus sign. Okay. Well, again, this is constant, so you actually had then E is some constant times V to the minus 2/3. Okay, so what would that then be? Well, the minus is going to cancel out, but that's going to give me 2/3 E over V. Okay. Well, that's interesting. And so let's rewrite that. Okay. You can solve for E. And so that's going to be E is equal to 3 halves P times V. All right. Well, we actually know PV is equal to, look, nRT. So that's actually 3 halves nRT. Great. Which now means we can actually figure out our specific heat. And remember my annoyance about V here, V is actually referring to it's the internal energy. And it's just the derivative of internal energy with respect to temperature, which is 3 halves nR. Okay. So that one's pretty easy. And then we could do sort of the next one and say, well, what's Cp? Well, that's just the E plus PV with respect to T. Well, come over here. What was E plus PV? Well, E was 3 halves PV. So this is, again, this is enthalpy. So that just means this is 5 halves PV. Okay, so that's easy enough. And so that just means this is 5 halves nR. Okay? And usually, again, depending how you define whether universal or not, a lot of times you'll just see this written as 3 halves R bar, and this is 5 halves R bar. And you got to depend on the notation, you got to check it out. So I'm going to drop the bars now and just call them R's, so I'm not always writing bars on them. And so you actually get the relation Cp is equal to Cv plus R for an ideal gas. So that's a super useful relation. Other useful relations, a lot of times you'll see when we start doing some different isentropic processes and things like that, you're going to get a lot of times an important ratio between the two. And this is often enough important, we actually define it as gamma. And so you're actually going to see here Cp over Cv is equal to 5/3 for an ideal gas. Okay, so this is also a very important relation. Okay? And if you take a look at this, and I'm going to come back to PV. Where is it from? Yeah. So E is equal to 3 halves PV. Okay. So I'm actually going to combine these two. And so that you will see P times V to the 5/3 is constant. Okay. So if V to the 2/3 times E is constant, and I just took E, the PE, I'm not worried about 3 halves, I get that's constant. Well, look at what I just showed below. That is PV to the gamma is constant. And so that's also another very, very, very famous relationship for some adiabatic processes. Okay? And so this won't be the first time we sort of play with ideal gas. I'll show you a few more times where it gets a little bit more familiar. But this is the nice thing about sort of deriving the ideal gas, again, from starting sort of like just this chapter 1 in a sort of a graduate textbook of statistical mechanics, or again, if you're coming from the physics world, this is the way you'll have seen it. But to know that things like equilibrium come from this sort of the total number of possible states, we then define entropy to have the right units, and then taking a natural log. And so we get things like temperature that come out of that. You get the equilibriums that come out of it. Sometimes your equilibrium is just temperature. Sometimes your equilibrium is volumes, or sorry, pressures are equal. And then from this ideal gas point of view, we can then actually count up the number of states in an ideal gas. Again, just billiard ball mechanics. It goes like volume to the n. And the cascade of that comes down to giving us this very famous relation for ideal gas. And we can kind of come back and, again, from the quantum mechanics of it and the total states, we can come back and get the relationships for specific volume, specific heat, constant volume, specific heat, constant pressure, specific heat, their relationships, the ratios, and as well some of these processes that we're going to see over and over and over for ideal gas. So we'll see you on the next episode as we dig back in some more.